Good evening, America. I'm Phil Sims.
And I'm Al Michaels.
Today we decided to take a look at physics behind what makes a tackle a tackle.
Helping us out, we have Aaron Rodgers out there on the field.
The Green Bay Packers.
Here at ESPN, we're very concerned about player safety, so we ensured that all the players out in the field were outfitted with the latest in sports technology protection.
Alright, now let's cut to live footage of our first type of tackle, the blindsided sack.
Here comes the, y'all don't really want it like, here comes the, y'all don't really want it like, here comes the, y'all don't really want it like, I said so.
Wow, what a hit.
Let's break it down.
The scenario that we are going to perform is if an 80-kilogram linebacker going at 2 meters per second sacks a 70-kilogram stationary quarterback, what is the final velocity of the two together? We're going to assume that this is a non-elastic problem and that the quarterback and the linebacker will remain stuck together up until they hit the ground. For this problem, we're going to find the final velocity the instant the quarterback and the linebacker meet. Our first step is to write down all the information that we know. We know that the mass of the linebacker is 80 kilograms and his velocity is 2 meters per second. And we also know the mass of the quarterback. His is 70 kilograms. And we're trying to find the final velocity of the two together. So we have to find the final velocity of the linebacker and the quarterback since they'll be stuck together. This problem is a conservation of momentum problem. This means that we can use the formula Pi equals Pf. As we all know, the P stands for momentum. But momentum can also be expressed in terms of mass times velocity. So we can rewrite the simple equation by using the variables, the mass of the linebacker, the velocity of the linebacker on the Pi side, and on the Pf side, the mass of the linebacker and the quarterback, and the velocity of the linebacker plus the quarterback. These two have to be together since the linebacker and the quarterback remain stuck together. Now that we know our formula, we can begin to plug in our variables. On the Pi side, we can plug in the mass of the linebacker, which is 80 kilograms, and we can also plug in his velocity, which is 2 meters per second. Now on the other Pf side, we have to plug in the mass of the linebacker plus the quarterback. This would be 80 kilograms from the linebacker plus 70 kilograms from the quarterback, and all that is multiplied times the velocity of the linebacker plus the quarterback, which we did not know and we are trying to solve. On the Pi side, first we need to multiply the 80 kilograms times the 2 meters per second. This gives us a total of 160. On the Pf side, we can add the 80 kilograms of the linebacker plus the 70 kilograms of the quarterback. This will give us 150. Now we divide the 150 from the Pf side and take it over to the Pi side. This gives us 160 divided by 150, and this will give us the velocity of the linebacker plus the quarterback, which is 1.07 meters per second.
Now let's see what happens to the tackle if the quarterback is in motion. Wow, what a hit.
Let's break it down.
The second type of tackle is a two-dimensional inelastic collision with a moving quarterback. If the 80-kilogram linebacker runs at 2 meters per second and sacks the 70-kilogram quarterback running at a 30-degree angle to the horizontal, what is the final velocity of the two together if the quarterback runs at 2 meters per second along the x-axis before getting sacked? First, we write down our values. The mass of the linebacker is 80 kilograms. The mass of the quarterback is 70 kilograms. The velocity of the linebacker is 2 meters per second, and the velocity of the quarterback is 2 meters per second. We're solving for the final velocity of the two together. Next, we can draw a diagram. The quarterback travels 2 meters per second on the positive x-axis, while the linebacker travels 2 meters per second going at a 30-degree angle to the horizontal, which leaves a negative y component and a positive x component. Now that we've drawn our diagram and written down our given information, we can begin with our equations. The initial momentum of both bodies added together is equivalent to the final momentum of them together. This can be written as Pi1 plus Pi2 equals Pf. This equation can further be written as the mass of the linebacker times the x component of the velocity of the linebacker plus the mass of the linebacker times the y component of the velocity of the linebacker added to the mass of the quarterback times the velocity of the quarterback equals the mass of the quarterback and linebacker times the final velocity. Now that we have our equation, we substitute in our known quantities into this previous equation. Simplifying this equation, we get 138.6 minus 80 plus 140 equals 150 times final velocity. The final equation is solved, and final velocity is found to be 1.32 meters per second. This value indicates the speed at which both the quarterback and linebacker are traveling after the initial collision.
Our final type of tackle is the head-on collision between the quarterback and the linebacker.
Waking up to ash and dust. I wipe my brow and I sweat my rust. I'm breathing in the chemicals.
Wow, what a hit.
Let's break it down. The third type of tackle that we are investigating is a head-on tackle between a moving linebacker and moving quarterback, resulting in an inelastic collision. If an 80-kilogram linebacker going at 2 meters per second tackles a 90-kilogram quarterback going at 2.3 meters per second head-on, what is the final velocity of the two if the linebacker holds on after making the tackle? From the question, we know that the mass of the linebacker is 80 kilograms, the initial velocity of the linebacker is 2 meters per second, the mass of the quarterback is 90 kilograms, and the initial velocity of the quarterback is 2.3 meters per second. We are trying to find the final velocity of the attached quarterback and linebacker. We can then draw a force diagram with the 90-kilogram quarterback moving 2.3 meters per second in the positive direction and the 80-kilogram linebacker moving 2 meters per second in the negative direction. After the collision, the quarterback and linebacker stick together and have a final velocity of unknown magnitude. Due to the conservation of momentum in inelastic collisions, we know that the initial momentum of the quarterback plus the initial momentum of the linebacker will equal the final momentum of the system. This means that the equation that we will use is the mass of the quarterback times the initial velocity of the quarterback plus the mass of the linebacker times the initial velocity of the linebacker is equal to the mass of the quarterback plus the mass of the linebacker times the final velocity. Upon substitution of the known values, we find that 207 minus 160 is equal to 170 VF. After simplifying, we find that 47 over 170 is equal to VF, or VF is equal to 0.28 meters per second.
Gotta forget what to say.
Forgot what I was going to say.